I'm Doug MacMartin from Cornell University, and I'm going to talk about stratospheric aerosol injection, or SAI, and put that a little bit in context with other approaches for solar radiation modification, or SRM. So the basic idea behind SRM is to reflect a little bit of sunlight back to space to cool the planet. And by a little bit of order 1% additional sunlight reflected would be more than enough to offset all of the warming observed to date. This would also act very quickly, making it a very powerful, potentially an additional tool that we could use in addressing climate change risks. So the basic idea behind SAI is modeled after what we see after large volcanic eruptions. So the picture here is of Mount Pinatubo in the Philippines. Erupted in 1991 and put about 30 megatons of sulfate aerosols into the stratosphere. In the tropics, that's about 20 kilometers above the ground, and there's a layer of very stable air where what you put there can persist for a year or longer, reflecting sunlight and cooling the climate. And Mount Pinatubo eruption is estimated to have cooled the climate by of order of half a degree for a year or two. It's a very robust effect observed after every large volcanic eruption. So the broad idea for SAI would be to do the same thing with aircraft. We do not currently have aircraft that can get that high with a payload, but it doesn't appear that it would be fundamentally hard to do. And so if you had a few $1 billion, you could go design an airplane, and for a few $1 billion a year, you could cool the climate. And that might be a lot of money to you or me, but in the context of climate change damages, that's not necessarily a huge amount of money. There's a few other ways you could do this as well. In principle, you could do something in space that's prohibitively expensive, almost certainly. Marine cloud brightening is the next most frequently discussed idea. The picture here is of ship tracks off of Europe's Atlantic coast. So that's formed by the pollution from a ship interacting with water vapor in the atmosphere to form a cloud. And you could in principle do that by spraying salt water into the clouds as well. This is less well understood. It's actually one of the biggest uncertainties in climate science is how clouds and aerosols interact. Stratospheric aerosols spread globally, so it's inherently a global solution. Marine cloud brightening is a little different in that you could do it in a much more targeted regime. That doesn't mean the effects would stay in a specific local area, but they could certainly be focused there. And in fact, Australia is looking at this right now for cooling the Great Barrier Reef. There's a third idea, which is cirrus cloud thinning. That's not actually reflecting sunlight, but avoiding trapping more heat. Cirrus clouds actually trap heat, so they warm the planet. And if you could thin them, that would allow more heat to escape. That's currently very uncertain, but it has similar governance issues. So none of these approaches should be considered as an alternative to cutting emissions. If you simply burned all the fossil fuels in the ground, you would need to keep reflecting more and more and more sunlight, and you'd need to sustain that for potentially thousands of years. However, we do not know today how rapidly we can drive our emissions to zero or what the impacts will be when we do. You can supplement emission reductions with pulling CO2 out of the atmosphere. But that is a difficult thing to do at scale, and we don't know how rapidly we'll be able to do that when none of those ideas are yet demonstrated at scale. And so there's a real possibility of having a significant overshoot of our temperature targets. That's the potential context for thinking about solar radiation modification, because we could very quickly cool the climate and maintain some desired temperature, for example. That said, it does not affect the climate the same way as rising CO2. And so the climate state that I've marked here at point 2 is not the same as the climate state at point 3. So just to illustrate that, here's one climate model simulation of SAI. On the left is the temperature and precipitation patterns that you get if you allow the temperature to warm by 1 degree from CO2. And on the right, what you get if you then offset that warming with stratospheric aerosols. And from a global perspective, this looks like it could be lower risk for almost everybody on the planet. 2 caveats. 1, this comes from a climate model, so there is, of course, uncertainty. And 2, people don't live globally, they live in specific places. And so, for example, in this simulation, there's a slight reduction in precipitation over India, that would need to be evaluated in context with the reduction in heat stress, for example. The other broad observation from climate models is that how you deploy the aerosols matters. So this is the same climate model. The only thing we did was we changed what season we put the aerosols in, and that affected the precipitation over India. The reason to point that out is simply that this is not one thing, and you cannot talk about the impacts of stratospheric aerosols. It depends on how you do it. And that makes decisions more complicated as well. So how would it affect the climate? Obviously, if we reduce sunlight, that will cool the climate, and the sign of that effect on many impacts, like Arctic sea ice, is pretty clear. But it does not affect the climate the same way as CO2. One obvious example is that it doesn't do much for ocean acidification. I already mentioned that it changes precipitation patterns, for example. There's potentially changes to ocean circulation. With sulfate aerosols, it can affect ozone, which would result in increased surface ultraviolet. Deposition, what goes up must come down. So in the case of sulfate aerosols, it comes down as acid rain. That's a small effect in places that currently have a lot of industrial pollution, but it could be a little bit more important in places that are currently pristine. There's a slight change to the seasonal cycle at high latitudes. And of course, there's always the possibility of surprises, although because we have the analog of large volcanic eruptions, there's at least some reason to bound that possibility. Bottom line for listing all of this is to say this is not really ready for deployment yet without more research to inform that decision as to whether or not it makes sense. And that research may involve lots of climate modeling, it may involve observations, and conceivably some very, very small experiments to understand, for example, stratospheric chemistry. That's a little bit about the physical climate side. The human dimensions are potentially even more important. So some key governance questions. How confident do we need to be? Who makes the decisions and how? That's probably the most important question. Whose voices are at the table? What happens if some places are harmed or perceived to be harmed? So that brings up issues of compensation and issues of monitoring and attribution. How do you ensure that this isn't used as an excuse not to mitigate? And related to that, to some extent, how do you manage the deployment for a very long time scale? Because if you ever stopped, the temperatures would shoot rapidly back to where they would have been without the stratospheric aerosols. So I will close there, and happy to take questions and look forward to an interesting discussion.